All right, so somebody asked me about some tough questions on recurrence relations and proving some results about recurrence relations. And so we have a recurrence relation defined like this, where uh, basically the next term is related to the previous term by multiplying by A and adding B. And so, depending on what A and B, you'll get lots of different types of patterns. Depending on what the first term is, you'll get lots of different possible sequences here. Okay. So, what we are told initially is that if A does not equal 1, then apparently this recurrence relation here can be written like this: un plus 1 plus c equals A times un plus c. Okay, so let's do it. What I notice is that my original recurrence relation is really similar to this, with the only difference that they added a plus c onto the left side. So what I'm going to do is add a plus c onto the left side of my original definition, and also add a plus c on the right side of my original definition. Then what I'm going to try to do is solve for what the value c has to be. So what I can say is that the A can be factored out here. So I have un plus b over a plus c over a. And that has to equal un plus 1 plus c. And so somehow we need to relate this new expression to the old expression. Okay. And so what I'm noticing is that my plus c here has to be equal to all of that stuff there. So I can pull that out and say c has to equal b over a plus c over a, which is equivalent, if you multiply by a, to saying a times c is equal to b plus c. If I'm trying to isolate c by itself, I can go a times c minus c is equal to b. Factor out a common factor of c to get c times a minus 1 equals b. And now I know that the value c is not really some third new parameter. It really is just b divided by a minus 1. So now I know that for any of these original, top left corner of the screen, for any of these original recurrence relations, I can actually just write it like this: un plus 1 plus c, which is b over a minus 1, is equal to a times un plus the same c, b over a minus 1. So there we go. We figured that out. Now, what we are told is that we are going to define yet another recurrence relation, and it's going to be in terms of u. So we are asked to consider a new type of recurrence relation, which is Vn, and that's related to Un. It's just Un plus c. Okay. So what are we going to do? We are going to write down a recurrence relation for Vn. Well, Vn plus 1 is Un plus 1 plus c, because I just iterated to the next term. But un plus 1 plus c should sound familiar. Un plus 1 plus c is this formula in the top right corner. And what that means is I can replace this formula in the top right corner with the right-hand side up here. So now I have this statement: Vn plus 1 equals a times un plus c. That's a u inside. I know the u's and v's are kind of hard to tell apart. But that looks familiar as well. un plus c turns out to be the very definition of Vn. So I can replace this last statement with V sub n plus 1 is A times Vn. And that means that the next term is the previous term multiplied by a constant. That's a geometric sequence. Okay. So what we're trying to do now is then write down an explicit formula. Well, if you have a geometric sequence, we know the explicit formula. The explicit formula is just the first term multiplied by the multiplier, the common ratio, raised to the n minus 1 power. And then we are trying to write down an explicit formula for un. Well, I remember that Vn was defined as un plus c. So now I know that un is just the same explicit formula that I found before, V1 times A to the n minus 1 plus C. Because, or did I do that backwards? Vn is un plus C. So the C is on the wrong side there. Sorry, let me fix that. I can switch it to a minus C. Sorry about that. Minus C like that. Okay. And what we need to do in one more step is write this entirely in terms of u, because we don't want to have this be in terms of v. So I have a v1 right there. But v1 is just u1 plus c. So un can be written as u1 plus c times a to the n minus 1 minus c. So we have written our recurrence relation in a completely different way. Then it asks us to think about a particular pattern, and a particular pattern that we have seen before is a pattern where the terms come out to be 2 to the n and then minus 1 at the end. So we are looking at a pattern, and the claim in the pattern is that, here's the claim in the pattern, that if u1 is equal to 1 and if u sub n plus 1 is equal to 2 times un plus 1, the claim is that the nth term is really just 2 to the n minus 1. Okay? And what we are going to try to do is show that that also works with this expression that we have right there. So let's just verify that it works. Our new expression says un equals u1 plus c. Okay, so u1 is 1. The c value that we found is just b over a minus 1. So b over a minus 1 is 1 over 2 minus 1. That gets multiplied by a to the n minus 1, which is 2 to the n minus 1. And then we are subtracting c, which is 1 over 2 minus 1. If you go through and calculate each of those pieces, you'll see that these parentheses become 1 plus 1. We have 2 to the n minus 1 and minus 1. Because this number inside the parentheses is another copy of 2, multiplying another copy of 2 makes the power of n, which checks out with the rest of the formula. So there were some problems where it's really easy to get mixed up in all the different letters. You've got A's, B's, N's, U's, C's, and V's. You've got lots of different letters. It feels like there's very few numbers floating around here. But just trying to always go back to what the definition is and then rewriting it in terms of the new letters. Let me know if you got any questions, and thanks for watching.